The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so welcome back everybody to AO3. Happy to see you again. So here is the current status of the AO3. So right now we have finished the discussion of coupled oscillator, and we go to infinite number of coupled oscillators, and we found that there's a wave equation coming out of it, and that means, in short, waves are really a group effort, right? So many objects are working really together so that they create a wave phenomena. And you can also see there's a close connection between vibration of a single object and the formation of the wave structure. Okay, so what we are going to do today is to give you a short review of what we have done last time. Then we actually will continue to our understanding of wave equation today. So what we have learned last time, we have learned how to solve infinite system with a space translation symmetry, and also we learned how to use it to solve finite systems by imposing or adding boundary conditions that will limit the infinite number of normal modes to finite number of normal modes based on, it's actually closely related to how many objects you have in the system. And also, we went ahead and go to a continuum limit, and we found that there's a surprising result coming out of this, and this is actually the wave equation. So what do we mean by going to continuous limit? So the limit we are talking about is that before, when we discussed discrete system of infinite number of objects holding together by strings, there is a length scale, which is the separation between objects, which is called A in my notation. And to make it continuous, we are taking a limit such that the A, which is the separation between objects, is so much smaller than the wavelength. Basically, the wavelength is actually the sinusoidal shape you see when I perturb a system. And what I'm assuming is that the distance between objects are so much smaller than the wavelengths. So that's actually what I call continuous limit. Okay, and that is actually true for most of the examples which we see in the previous lectures. For example, I was holding a giant spring, and I oscillate that, and all the little components, or say all the little mass on that spring, the space between all those little mass on the spring are so much smaller than the length scale we are talking about, which is at the order of 1 meter, right? Okay, so that actually is a sensible limit which describes the physics we are interested. When we do this, when we go to a continuous limit, we found that there's something really interesting happens. N-1K matrix originally is a infinite times infinite dimension matrix. It becomes an operator, which is actually minus t over rho L partial square partial x square. And also, okay, I changed the notation here. It was AJ, and I changed it to psi because what we are going to use in the later round when we describe wave functions, etc., especially in AO4, we usually use psi and the psi j, which were discrete and evaluated in the individual discrete position in the x direction. It's becoming a continuous function, which is psi x, and it's also a function of t. Okay. Therefore, from this exercise, we found that we see a wave equation actually after we go to continuous limit. And for more information, you can also take a look at the the textbook in the relevant page. So what are we going to do today? So today, what we are going to do is to understand the wave equation, the structure, and what does that mean, and also what are the normal modes coming out of this wave equation. And the next time, in the later lectures, we will also discuss another special kind of motion, which is progressing wave solutions. Okay, so that's immediately get started by looking at a concrete example and also to derive the normal modes from this wave equation. Before we do that, let's take a look at this wave equation. Okay, this wave equation is actually equivalent to infinite number of equation of motion. Right? If you think about it, why is that? That is because each x, okay, each position x you put in will produce an equation of motion, right? So basically, originally we were when we were doing a discrete case, those are labeled by J, right? J is actually it's actually telling you which mass I'm talking about. Now it's actually replaced by x. And what we are actually doing is to solve infinite number of equation of motion in one go, and that is actually the wave equation. So the first question we ask is, okay, what is actually normal modes based on this infinitely long system described by infinitely long continuous system described by wave equations? So let's get started immediately. So basically, we can first assume what is actually a functional form for normal modes, right? So what we can actually do is we can assume that psi xt is actually equal to a is actually a function of x times b is actually a function of time. Okay, so what I'm doing is actually have a meaning actually. So a of x is actually giving you a description of the functional form, the shape of the, for example, the shape of the normal mode as a function of x, right? So that's actually giving you the shape as a function of x-axis. Okay, and b, which is a function of t, is actually giving you information how individual component goes up and down or move as a function of time. Okay, so that actually controls the time evolution. And we were using this wave equation to describe a continuous system, like, for example, a string with tension T. Okay, so what we could do is the following. So we are interested in the solution of the wave equation, which is shown there. So what we could do is that, okay, let's first assume this functional form, assuming that every component is actually following the same time-dependent evolution. And then we can actually plug in this functional form to the equation of motion and see what we will get. So if we plug this into the wave equation, so what we are going to get is, if we look at the left-hand side, it's actually a partial derivation with respect to time. Therefore, what we are going to get is a of x times partial square b, it's a function of t, partial t squared. The right-hand side of the equation, which is actually equal to vp squared, okay, is a partial derivation, a partial derivative with respect to x, okay. Therefore, you have b is a function of t only times partial square a of x partial t squared. Okay, so actually we can for convenience. Oh, sorry, to be partial x. Thank you very much. partial x squared, okay? So just for convenience, actually we can actually divide the whole equation by a times b times vp squared, right? Okay, we can actually divide by the whole equation by a times b, for example, and the vp squared. If we do this, then basically I'm moving this part to the left-hand side, so I get 1 over vp squared b of t partial square b t partial t squared. Okay? And the right-hand side, because I also divide ab vp squared, therefore I get 1 over a of x partial square a of x partial x squared. Okay? So far so good, and basically what I'm doing is just plugging the functional form which I assume here, and divide everything by ab times bp squared. And what I immediately find is that left-hand side is a function which only depends on t, right? Left-hand side only depends on t, okay? And right-hand side is a function which only depends on x, okay? So in short, I have in this situation f of t, which is left-hand side, is equal to g of x. You will see this over again in the later lectures related to physics. This is actually so-called separation of variables, right? So basically, you are facing a situation f of t equal to g of x. Okay, if you think about this situation, that's actually really, really helpful because, okay, now I can, what I can do is I can stay at a specific x, okay? For example, I choose this point, okay? Then I let the time go forward. Okay, of course I cannot stop the time, right? But it's going, if it goes forward, then left-hand side equation, if it's changing, it will change, right? Because I changed the t. Okay, if the left-hand side equation is changing, then that's actually not going to, this equation is not going to work, right? Because I'm not changing x. I'm fixing myself at a specific location, and let the time go on. Then if left-hand side is changing, then this equation cannot work. You see? Therefore, what is the consequence of this equation? That means left-hand side, f of t, must be a constant, right? Therefore, no matter what I do, if I change time, it's not going to change anything. I can put in whatever time, like 1 billion years after this lecture, or now. It doesn't matter, right? It's a constant. So it must be a constant. Okay? I can do the same trick, okay? I froze the time, okay? I fix the time, and then I compare this point to that point, or say something billions of light years away from this classroom, okay? I'm changing the x, but I'm not changing the t, okay? The same argument also holds. If this function is changing the function of x, then I'm screwed because it doesn't work, right? I mean, this, right? Therefore, it has to be a constant also as well, right? Okay, constant is equal to a constant. That's lovely. That's really lovely, right? That means I can say this is equal to that is equal to a constant. Okay, as usual, I call this constant really strange fancy name, minus kn squared, which you would not like it, but later you will like it. Okay. Okay, very good. So we make tremendous amount of progress originally, we thought that we are in trouble. It's a times bt, ax times bt sounds really horrible. Now, actually, you see that this equation is really simple to solve, okay? Okay, so let's actually take a look at the solution to the f function and the g function, okay? So the first thing, if I take the left-hand side, which is a time dependence part, okay, I can copy there. It's actually copy the equation here. It's 1 over vp squared b of t partial square bt partial t squared. And this is equal to a fancy name of this constant minus kn squared. Okay? And of course, I can multiply everything by vp squared b. Then I get partial b squared b partial t squared. And this is equal to minus vp squared km squared b. Wait a second. We have solved this equation infinite number of times, right? In this lecture, right? Okay, right? You remember the solution? What is the solution? Anybody can help me? Anybody? It's sine or cosine function, right? It's harmonic oscillation. It's almost like equation of motion of a spring mass system, right? Okay, I hope that you are already bored. Then that means I'm very successful. B of t will be equal to B of n sine omega mt plus beta m, where omega m is actually equal to Vp times Kn. Okay, I define omega m equal to Vp times Kn. Okay? All right? So, surprisingly, the solution of B is really simple. It's actually Bn sine omega mt plus beta n. So what does that mean? That means the overall motion or overall time-dependent evolution of the system is like harmonic motion if you look at individual component, okay, in this system, okay? So that's really nice. So let's take a look at the right-hand side. The right-hand side, what we have is 1 over a times a of x, partial square a x, partial x squared, and that is equal to minus km squared. Okay? I don't want to go over this again, right? This is actually the same thing as number 1, right? The only thing which is different is that now the partial derivative is actually, it's actually x, right? It's partial square a partial x squared. Therefore, I can immediately write down the solution. A of x will be equal to Cm sine Km x plus alpha n. Okay? Any questions so far? Okay. So until now, you accept the fact that f of t and the g of x has to be the same constant. And I call it minus km squared. Okay? And I didn't actually tell you what km I'm choosing, right? In reality, according to this result, Km can be anything, can be any number, as long as it's a constant, right? Therefore, I would like to write the corresponding psi, which is the wave function, is actually labeled by n, okay? N is actually just label which k I was using, okay? Nothing fancy, it's just a label. Psi of n is a function of x and the t, okay? That will be equal to Bn times Cn sine omega mt plus beta n sine kn x plus alpha n. Bn and Cn are just arbitrary constant, right? Therefore, I can actually merge them, and I will call it just An. And of course, don't forget, we have this condition. Omega n is actually equal to Vp times Kn. Okay? So this is actually defined here. Okay, so here, since this is actually a second order differential equation, you have unknown factor, which is beta n. You have also Bn as an unknown. And the right-hand side, you also have a Cn, which is unknown, and alpha n, which is unknown. Okay? When we combine them, I replace Bn times Cn by An. Therefore, what we have is that An is actually some kind of amplitude, which can be determined by initial conditions, which I will talk about that later. Beta n is the unknown coming from the left-hand side deviation. Alpha n is also unknown, which is actually coming from the right-hand side deviation related to the shape of the normal mole of the system. Okay? And finally, there's one additional unknown coefficient, which is Kn. It's kind of arbitrary now. Control actually the wave number, or say the wavelength of the shape of the normal mole. Okay? So when you see this, doesn't this surprise you? May not surprise you anymore, right? Because we have solved infinite number of coupled oscillator. And you have learned that, okay, the normal modes have a shape of sine function. It's like a sine function. Before it was like a sine at jka, right? And the ka is becoming x. So what we are actually getting here is that, doesn't surprise you, since this system also satisfies space translation symmetry. Therefore, the functional form of the shape of the normal mole is also a sine function. Okay, so that's actually pretty satisfactory, and also come out as what we would expect based on what we actually have learned. Okay, so let's actually take a look at the structure of this function. So basically, as I mentioned before, everything is oscillating at the frequency omega n and with a phase beta n. So that satisfies the condition of normal mode, right? What is the condition? All the components in the system are oscillating at the same frequency, at the same phase, okay? Indeed, yes, that's correct, right? Also, as a function of time, it's actually going up and down harmonically, as we already discussed. And the relative amplitude, as I said, is a sine function. And of course, I already demonstrated this before, that you can see that in this system, you can see a sine function when I start to drive it. So what I'm doing is actually to convert the kinetic energy from my hand to energy stored as potential or kinetic energy in this string rod system, in this bell wave machine. Okay? So you can see that beautifully, those are sine function. And of course, if I do a higher frequency one, you can see that, the oscillation frequency changed, right? And that is actually controlled by this equation, this dispersion relation, okay? And this dispersion relation is actually relating two physical quantity. One is actually the wave number. Of course, if you are more familiar with wave length, it's actually 2 pi over kn. Lambda m is actually the wavelength of the shape of the normal mode. And the oscillation frequency is actually controlled by this dispersion relation, okay, this function. And you can say that, Professor Lee, I have been so tired of this demo, okay? I've seen this 1,000 times, right? And basically you are showing me that, okay, you can actually oscillate this system and excite this system so that it's oscillating at some natural frequency this system like, right? It's actually some kind of resonance behavior, right? So I can actually excite, I can randomly shake this system, and it's going to be a linear combination of all the excited normal modes, right? We have seen this many, many times. What I'm going to show you is that there's another machine here, which is actually demonstrating resonance of sound wave, okay? So here is actually so-called it's called a Rickett tube, okay? So the structure is like this. So basically, you have a metal tube, which is the resting there, okay? And inside the tube, you cannot see it now, but inside the tube, there's a wire mesh, okay, which the air can flow freely up and down in this mesh, okay? And what I'm going to do now is to heat up the mesh and see what is going to happen, okay? I will just heat it up by like 6 seconds and see what is going to happen. So now I'm going to do this very carefully. Can you hear that? Okay, very good. All right, so listen, what is happening? So you hear a mono frequency sound, right? Generated from what? Generated from the heat I give to the wire mesh, okay? So what is actually happening? So when I heat up the mesh, okay, what is going to happen is that the air around this screen is going to be heated up, okay? Therefore, because the air is heated up, it goes in the upper direction. And also the volume of the air is expanding, okay, because of the increased temperature, okay? And that will actually go through this system. And what it does is really like what I'm doing to the Bell Lab wave machine. It's actually trying to oscillate or excite any possible normal modes which this system actually like. Okay, so you can see that after a while, once the pressure and also the air inside the tube get then self-organized, then you hear a very loud sound. And also so that means there are energy flowing from the tube to your ear, and that is actually coming from what? Coming from the heat I put into this system. So it's actually a heat sound wave conversion, okay? So I hope you enjoyed this demo, and we will take a 5-minute break to take questions before we move on. And of course, you are welcome to come here and to play with the demo. if you want. Okay, so welcome back from the break. What we are going to do next is to understand how to determine all those unknown coefficients, right? So you can see here there are Am, which is the amplitude, okay? There are beta M, which is actually the phase, Km, which is actually the wave number, and the alpha M, which is the phase for the shape. Okay. So what I'm going to show you is that Am and the beta M, okay, these two quantities will be determined by initial condition. While Km and the alpha M, okay, as you may guess, those can be determined by boundary condition. For the Km and the alpha M, okay? So why don't we just immediately get started with a concrete example? Okay, so let's take a look at the situation. Okay, so this equation, okay, and also all the possible Kn are allowed when we talk about infinitely long system, right? So far, we have not imposed any boundary conditions, okay? And what I'm going to do now is to show you an example boundary condition and see how we can actually fix Kn and alpha n. So suppose we are interested in this system. So I have a wall in the left-hand side, and I have a string with length L, okay? And it's actually connected to a massless ring. Okay? And this ring is actually can actually move up and down along the rod in the right-hand side. Okay. And I also assume that this string have a string constant, have a constant tension T, and also the density rho L. So basically, it's a mass per unit length. Okay, so that's a system which I'm interested, and of course, I need to define my coordinate system, right? As usual, I define horizontal direction to be x direction, and I define the vertical direction to be y direction. And I define y equal to 0 is the equilibrium position of the string. When psi is equal to 0, that means this string is actually at rest and not moving with, it's actually in the equilibrium position. It's not displaced at all with respect to the y equal to 0. And I can also define that x equal to 0 is the position of the left-hand side wall. Okay. So this is actually the physical situation, and I would like to actually find out what are the boundary conditions, right? So what are the boundary conditions? So from what we actually discussed last time, left-hand side, since this string is actually fixed on the wall, right? I nail it there, cannot move, right? Therefore, what is actually the first boundary condition? What is actually the first boundary condition? Anybody can tell me? Which describes the situation, the physical situation in the left-hand side. Y0 is 0. Very good. So when x is equal to 0, y0 is 0. Okay, so on my note, I was using a different notation, so I will just use psi. Okay, so psi 0 is equal to 0. Okay, apparently, there's another boundary of this system, okay? The other boundary condition is actually happening at x equal to L. What is actually the boundary condition? Can somebody help me? Yes. The derivative of the psi is equal to 0. Okay, so we will explain to everybody why is that the case. Okay, the answer proposed is that partial psi, partial x, L, t is equal to 0. And this is 0 t, right? Because that has to be true no matter when I actually visit this boundary condition, right? Okay, so what is actually giving us this strange boundary condition? Okay, so suppose I focus on the force diagram on this ring, okay? So this ring is actually connected to a string with string tension T, right? Okay. There's another force which is actually trying to balance the string tension, right? Which is the normal force. Okay, normal force coming from the rod, which is actually trying to stop the ring from moving in the horizontal direction. So there is a normal force. Okay. And we also know that this ring is actually massless. So m is equal to 0. Okay. Suppose that this partial psi, partial x, the slope is not 0. Okay. If slope is not 0, that means the string may be pulling this ring to some direction. Okay. What is going to happen? So if this happens, okay, it is actually clear that the normal force cannot balance the string force, right? Everybody get it? What will happen? If this happens, then this massless ring will suffer from infinitely large acceleration, right? Because F is equal to NA, and N is 0, so A goes to infinity. So that means this ring will disappear, go to the edge of the universe. Did that happen? No, it didn't happen, right? Therefore, this condition must be satisfied. You see? So the slope of the string cannot be non-zero. Otherwise, some crisis will happen, right? Okay? Okay, very good. So we have the two conditions. And the second thing which we are going to demonstrate you is that, okay, I promise you that boundary condition can fix these two constants, right? So therefore, we are going to demonstrate that. Okay, so let's use the first condition we have in the right-hand side board. And basically from 1, you can actually get psi n 0t. Okay, I am plugging in this condition, okay, plugging in this solution to boundary condition number 1. And basically what I'm going to get is this is equal to an sine alpha n sine omega nt plus beta n. Okay, and this is actually equal to 0. Okay, so you only have an alpha m here because I am setting x to be equal to 0, right? And setting x to be equal to 0. Okay, therefore you only have that functional form. Okay, so now we are facing a choice. So you can set an to be equal to 0, it's an arbitrary number. But if you set an equal to 0, everything is 0. It's not fun, it's not moving, right? Therefore, I don't want to set an to be equal to 0. Okay? And you can say that, maybe this is equal to 0. Sine omega mt plus beta m is equal to 0. But this is actually a sine function, and this condition has to be satisfied no matter which at which time you are revisiting this boundary condition, right? At all time, this boundary condition has to be satisfied. Therefore, this cannot be equal to 0. Okay? Therefore, I conclude that this is equal to 0. Okay? So what does that mean? That means I can choose alpha n is equal to 0. Okay? So that's actually given by the first boundary condition. So let's actually take a look at the second boundary condition, partial psi, partial x, evaluated at x equal to L, and any time t is equal to 0. Okay, so now I can plug in again the solution in the middle board, partial psi n, L, t, partial x, and that will be equal to an, kn, sine omega mt plus beta m cosine knx. And this is equal to 0. Okay? So I'm taking a partial derivative, partial psi, partial x. Therefore, the sine becomes cosine. The sine of knx plus alpha n becoming cosine. And also, I know already from the first boundary condition, alpha n is equal to 0. Okay? Therefore, I get cosine knx here. Okay? So, and this is actually evaluated at x equal to L, right? So that means this thing must be equal to 0 based on the second boundary condition. Okay? Of course, we can have the same argument. An should not be equal to 0. Otherwise, it will be equal to 0 all the time. The whole wave function is 0. Okay? And this is actually changing as a function of time, the same argument, because this boundary condition has to be satisfied at all time. Okay? From the beginning of the universe to the end of the universe, this condition has to be satisfied, right? Therefore, this cannot be equal to 0. And what is actually left over is cosine kn x evaluated at L equal to 0. So cosine kn L is equal to 0. Okay? So that means you cannot arbitrarily choose kn anymore, right? Before we introduce boundary conditions, we were saying, kn is actually some arbitrary constant, right? And now it's not arbitrary anymore. It has to satisfy this condition. Okay? What does that mean? This means that kn has to be equal to 2m minus 1 divided by 2l times pi. Okay? You can actually check this. And this small n is equal to 1, 2, 3, etc., etc. Okay? And it can be, you can see that there are many, many different solutions. Okay? So you can see that, as I mentioned before, the boundary conditions determine kn and alpha n, right? So you can see that the first condition at x equal to 0 determine alpha n. The second boundary condition also help us to determine what are the possible kn value, and that is actually listed here. Okay? Any questions? No? Okay. So in order to help you to visualize what we have learned from here, I can now choose n is equal to 1. Okay? So you can see that I carefully choose my notation from the beginning, right? So therefore, m is now the index of the normal mode I'm referring to. Okay? So now, if I choose m equal to 1, then I can actually evaluate what will be the resulting k. So the k1, okay, according to log formula, 2 minus 1 is giving you 1. Therefore, you get pi over 2l. Okay, and of course you can also calculate based on the wave number what will be the wavelength, right? So the wavelength lambda 1 will be equal to 2 pi over k1, and that will give you 4L. Don't forget, once you actually already decide the k, the omega is also determined, right? Because omega, which is the angular frequency of this normal mole, is determined by that dispersion relation omega n equal to Vp times Kn, right? So therefore, I can now calculate omega 1, that will be equal to Vp times K1, and that will give you square root of T over rho L pi over 2L. Okay? So this is actually coming from the last lecture on the formula of Vp. Okay? So that means if you fix the shape of your normal mole, then the angular frequency is also fixed according to this dispersion relation. Okay, so of course I can now visualize this situation. Then basically I can plot this system as a function of time, as a function of x, not as a function of time. So when this system reaches the maxima amplitude, it will look like this. And this is actually amplitude A1, right? Because when I'm talking about the first normal mole labeled by m equal to 1, and there's an unknown amplitude A1, and that is actually shown here. Okay? Of course, I can go ahead and calculate if n is equal to 2, what is going to happen. If I increase the n, what is going to happen is that k is also increased, right? Okay? So k is increased, then that means the wavelength is decreased. I have calculated the k for you, and that is equal to 3 pi over 2L. And also the lambda 2 will be equal to 4L over 3. You can actually double check this at home. And of course, I can now demonstrate what will be the resulting shape of the normal mole. It will look like this. And this is actually telling you the amplitude A2. You can also do n equal to 3, right? If you do that, basically what you get is something like this, etc., etc. Okay, any questions? And the motion of this system as a function of time is that this whole shape, is multiplied by sine omega mt plus beta m, right? So the whole shape is going to scale up and down harmonically, okay? And so if you focus on one of the points here, it's going to be going up and down harmonically. Very important, there's no back and forth movement. Everything is only moving up and down. If you focus on only one of the particles in this string, okay, everything is moving up and down. Like here, right? So when I create a curve, when I create some kind of wave, all the components are always moving only up and down instead of back and forth, right? Because they can't move back and forth. But you may be cheated by the shape, evolution of the function of time. It seems to me that something is actually moving back and forth, but never. All the particles are moving up and down. Very important. Finally, we have shown you the first 3 normal modes, and what is actually the most general solution. What is a general solution? Of course, as we had before, general solution would be a linear combination of all the possible normal modes. So now I would like to write psi xt as the general solution. It's going to be the sum of all the allowed normal mode. In this specific case, okay, it's going to be a summation of from 1, m equal to 1 to infinity, am sine omega mt plus beta m sine km x plus alpha m. And in this specific case, it becomes cosine. The km is there, right? Cosine 2m minus 1. Oh, sorry, it should be sine. It should be sine 2m minus 1 over 2l pi, and the alpha n in this case is equal to 0. Okay? So the upper formula is the most general case. You're summing all over the possible m's. And the km and alpha n can be determined by boundary conditions. And in this specific case, the right-hand side expression is written like sine 2m minus 1 over 2l times pi. OK, so that's very nice. And you can see another set of examples here in the slide. So this is another set of normal modes from m equal to 1 to n equal to 6. And you can see that in this example, both ends are fixed. Okay? Instead of one end is actually floated, attached to a massive ring. If both ends are fixed, then you get this normal modes. And of course, in the later in your P set, you will be exercising this kind of normal modes and solve the corresponding Kn and alpha n. And you can see that if you focus on the upper left corner, you will see that the oscillation frequency is low, right? Why is that? That is because the wave number, Kn, is small, therefore wavelength is long. According to that formula, omega n is proportional to wave number. Therefore, you can see that the oscillation frequency is actually 2 times slower compared to m equal to 2 case, which is the upper right corner result. And you can see that if you increase n more and more, you get larger and larger k, and therefore you see that the oscillation frequency is getting larger and larger. Okay? So, all right. So now we are actually facing an issue here. Wait a second. So now we have solved the normal mode, the functional form of normal mode. We have learned how to determine Km and alpha m, right? But we are facing a difficulty here because Am is very difficult to solve because you have infinite number of terms here, right? And the beta m, how do we solve this, right? So it's getting really, really difficult. So what I'm going to tell you is that we can actually, again, use the help from the math department. They have actually proposed the solution. Okay, they actually say that, this is actually identical problem as we solved in the math department. It's just Fourier decomposition. Okay, and Fourier series. So what is actually Fourier series? So you can see from here, there's a triangle and triangular shape between 0 and 1. It's a function plotted as a function of x. And between 0 and 1, it looks like a triangle. And if you do a Fourier decomposition, it can be decomposed as small k sine function plus the second normal mode and plus a third normal mode. And you can see that if you increase the number of terms included in this Fourier series, then you will see that the shape is actually getting closer and closer to the triangular shape. Okay. In order to help you with the visualization. Here is actually what I prepared. So, okay, so this is actually extractive from, it's actually a real example which I really use computer to calculate, and I extract the contribution from n equal to 1. This means that the first term in this summation, infinite number of term summation, okay, the first term looks like this. And if you include the first and second and third term, it becomes something like a plateau. And if you increase 1 to 5, it's evolving as a function of n, becoming more and more strange shape, right? And this is actually including the summation from first term to 11th term, right? And finally, 11 to 19. What is this? What is actually the function I put in? It's actually a NIT function. I put in a NIT function into this again, and you can see that, wow, from 1 to 59 turns, I need to use 59 turns to describe this really wonderful shape, right? Okay, so in order to help you with the visualization, you can see I prepare a little program which actually can show you the evolution as I increase more and more m turns. Let's take a look. You can see that originally it doesn't look, oh, you cannot see anything. Wait a second. What is going on? Let me see if I can. I hope I don't screw this up. Okay. Sorry, I need to restart. Okay, so let's get started. So you can see that from the first few turns, it doesn't look like anything, but very soon, when you have 20 turns added to each other, they look really pretty much like a NIT dome. And you can see that this program is really trying really hard to describe the sharp edge at the left-hand side and right-hand side, right? You can see that those kind of really infinitely sharp edge will need infinite number of turns, so that, you know, if your m is really huge, then the k, the wave number, is going to infinity, then you can actually produce infinitely sharp edge, okay, in this function. And that is actually, you can see from this demonstration, the program is really struggling with this really super sharp edge. So look at the left-hand side and right-hand side corner. Originally, the slope is clearly not high enough, and as we include higher m value turns, and you can see that the description becoming much better at the edge. But of course, still not perfect, because you need infinite number of turns to describe the shape of an NIT dome. Of course, we can also take a look at other example. Just testing my eyesight. I'm not sure if okay, so I can increase the speed to save down time. So this is actually a square pulse, which you can see it from the scope pretty often when you do experiment. And you can see that a square pulse is really difficult to reproduce, as I said before, due to this sharply rising edge. And of course, I can also demonstrate you another example, which is a triangular shape. And you can see that still, you can see it works pretty nicely. And the function doesn't like at all the right-hand side edge, right? Because of the same, exactly the same reason. Okay, very good. So let's come back to the presentation. Can you see? Okay, very good. So the question is, how do we actually extract AN and beta N, right? Okay, I have done that with a computer program, and what I'm going to do now is to show you a concrete example, and we are going to go through them together to see how we actually can extract AN and beta n. So suppose I give you an initial condition, okay? It's exactly the same system I'm talking about, but now I prepare this system at t equal to 0, some specific kind of shape. Okay, this L over 2 is actually the first half of the system is actually untouched. The first part of the string is actually at the equilibrium position, and this is actually x equal to L over 2. Suddenly, I actually move the string sharply up, and the rest half of the string is actually at the height of h in this case. And of course, the right-hand side edge is equal to x equal to L. Okay? And this is actually a snapshot which I actually took with my camera at t equal to 0. Okay? And also, I assume that at t equal to 0, the string, all the components of the string, okay, is at the rest. Okay? So based on this information, which I give you, I can now translate this information into mathematics. So that corresponds to two initial conditions. The first one, okay, is that since the string is at rest, that means psi dot x evaluated at t equal to 0 is 0, right? Because the string is at rest. Okay. The second initial condition is that psi x0 is known. And it's actually shown in this graph. Okay? So from this, we would like to see if we can actually extract information about capital N, capital AN, and the beta N. Okay? So that's immediately get started to see how we can use those initial conditions. Okay, so from the first initial condition, A related to the initial velocity of the string, okay, basically we can get psi dot x t, and this will be equal to basically sum over n equal to 1 to infinity. So basically, I'm taking this equation, okay, when I plug in that equation into the first initial condition. So basically what I have is an omega n sine omega m t plus beta m. Oh, this will become cosine, I'm sorry, because I'm doing a derivative, right? Psi dot, so this will become cosine, right? And the sine km x plus alpha m. Okay? And this is actually equal to 0 when psi dot x t is actually evaluated at t equal to 0. Okay? And this is equal to 0. So if I plug in t equal to 0 to this equation, this becomes 0. Okay? And we know that the shape of the normal mode is some kind of sine function from the previous discussion. Okay? And I am now requiring this thing to be equal to 0. Okay? Of course, I cannot make an omega n equal to 0. That's what we discussed before. And this sine function can be evaluated at any place of any x value. Therefore, this cannot be equal to 0. Therefore, what is actually the result? The resulting condition is that cosine beta n will be equal to 0. Right? Therefore, from this initial condition, actually I can conclude that beta n is actually equal to pi over 2, for example. Okay? All right? So therefore, you can see that very clearly from the first initial condition, the string is not moving at the beginning. I can conclude that beta n is equal to pi over 2. Okay? And just a reminder, alpha n is actually equal to 0 from the previous discussion, and the kn is actually equal to 2m minus 1 pi divided by 2l. Because I just want to copy here because somehow the board is covered by another board. Okay? So now I have done with the first initial condition. And the other initial condition I have is that, okay, I provided you the picture I took at the beginning of the experiment. Therefore, psi x0 at t equal to 0 is none. Okay? So, very good. So I have this condition, but now I'm facing a difficulty because all those terms, okay, all the terms n equal to 1 to infinity contribute, right, as we demonstrated before, to this shape. Okay? It's very difficult to actually evaluate an. Okay? So the trick is that to make friends from the math department. So what we could do is that we can use the orthogonality of the sine function to overcome this difficulty, right? So let me immediately write down what do I mean by orthogonality of the sine function. So if I do an integration from 0 to L on that dx sine kn x sine kn x, okay? If I do this integrating from 0 to L, so what I'm going to get is that basically you either get L equal to 2 if n is equal to n, or you get 0 if n is not equal to m. Okay? So basically, I have two sine functions multiplied to each other, and I do an integration from 0 to L multiplied by delta x. And this is kn, this is kn. If kn and kn are different, okay, based on, you can actually go ahead and do this exercise, and you will find that indeed, if they are the same, then you will get L over 2. On the other hand, if they are not the same, the k values are not the same for the first and second sine function, you are going to get 0. Okay? So that's a very good news. Because if I do this calculation, I do 2 over L integration from 0 to L psi x0 sine kn x dx. Okay? What is going to happen if I do this integration? Remember, psi n is a linear combination of infinite number of normal modes, right, with different sine kx, kmx, right? Okay? If I multiply that by sine knx, okay, this is a very crazy thing to do because all the other terms will become 0 if the k value of one of the terms is not equal to this dictator's value kn, it's 0. Okay? Otherwise, it's L over 2, and it is designed here to cancel that factor. Okay? So you can see that this is like a mode picker. I'm picking up a mode with this tool. This is like this tool. I'm picking this mode, which is actually matching my Kn. Okay? It's a miracle that this become Am. Okay? I hope you get this idea, even if probably you haven't heard about Fourier decomposition before. But essentially what we are doing is that I'm going to evaluate infinite number of integral, and you are going to do that in the exam. Okay, hopefully easy. What is going to happen is that if you do this integral, you are going to pick only one mode out of it, and you are going to be able to know the amplitude of that mode. Okay, so let's do this immediately in this example. Okay, so Am is actually equal to 2 over L. Okay, since the amplitude is actually 0 between 0 and L over 2, right? So I can safely just integrate from L over 2 to L, right? Okay, so I do an integration from L over 2 to L because between 0 and L over 2, the amplitude, the initial position is 0, okay? All right, so what I'm going to get is h sine Kn x dx, okay? And of course, everybody know how to do this integral, right? Doesn't look that horrible. And this will become 2 over L minus h over Kn, okay? And basically this will become cosine Kn evaluated at L minus cosine Kn evaluated at L over 2, okay? And where this Kn, as just a reminder, is actually equal to 2n minus 1 pi divided by 2l. Okay, so I hope this actually help you to understand the procedure to determine all those unknown coefficients starting from this equation. Am and the beta m can be determined by initial conditions, as we actually show here. You can use the initial condition of velocity and the initial condition of the shape and the help of a mode picker to pick up the amplitude from that tool function. Okay, and also you can see that Kn and alpha n related to the shape of the normal mole can be determined by boundary conditions. Boundary conditions, how this system is actually connected to the nearby systems, right? The nearby systems are the rod and the wall, right? So that is actually the two boundary conditions which determine the shape of the normal mole. And finally, very important, as usual, the most general solution is, of course, the linear combination of all those possible normal mole from m equal to 1 to infinity. And omega n, don't forget, is determined by the dispersion relation Vp times KL. Before the end, I would like to mention to you something which you might actually not notice when we were discussing this. So you can see that omega is now proportional to Kn. Okay? So if you plot omega as a function of K, actually you can see that it's becoming a straight line, okay, in this graph, which is very straightforward. And on the other hand, if you remember what we get last time with discrete system, okay, with length scale, the length scale between little mass is actually a, you get omega squared is equal to 40 over m sine squared Ka over 2. Okay, so if you plot this as omega as a function of k, you get the black curve. Okay, what does this actually tell you? That is actually telling you that if you prepare a system at a specific normal mode, based on the oscillation frequency, you can actually know the internal length scale of the individual mass. Okay, just in case if you didn't notice this interesting fact. Okay, so thank you very much. I hope you enjoyed the lecture, and I will see you next Thursday, not here in the Walker room. Okay, Walker Memorial. So good luck, everybody. Maybe see some of you in the office hour tomorrow.